Alright, so this is like an intro video to Cybin or something. It's probably going to sound really weird because I'm like half whispering because I don't want to be super loud. I also don't know if I'm even going to end up using this, but I guess we'll see. So Cybin is like a Lua REPL, but wrapped in Jack or libsound.io, I guess, if you're on a really old version that still has OpenGL support, which was a bad idea. And instead, I'm going to make a separate thing that Cybin can communicate with for graphics eventually. But the idea is that you have a single function called __ process, and all audio and MIDI and every event flows through that, and all of the audio processing and any actual meaningful work is done by Lua. And any Cybin script can be run in real time or it can be run offline, and it will just render out to a file. So you could write music live and then render it offline seamlessly without having to do pretty much anything else. So right now I have Cybin open in Emacs. We have a REPL here. So read eval print loop means that you read some stuff. So you can see like 1 + 1 here. We evaluate it. Well, actually I should have done print. It evaluates and prints and loops. We can do that again. And we have some shortcuts. So if you hold down control and hit C while holding control and then E, it evaluates a whole block. So that just tried to connect Cybin to our outputs and Cybin to FFmpeg, which is recording this. You can see over here, FFmpeg's up here, and you can see all the connections over here, or actually over here as well. Everything's hooked up. So Cybin's get 2 audio ins and 2 audio outs, and 2 MIDI ins and 2 audio outs, 2 MIDI outs. So the only thing you need to do with Cybin, and it does come with some standard libraries that are all Lua, but you don't need them. You can just define a function called process, and that's going to be frustratingly hard to see. I might need to fix that eventually. And it's going to return a value, and so it's returning 0, so we're hearing nothing. But if we return math.random and we multiply it by some small, divide by 20 so that we don't blow our ears out. So you can see really easy to get sound working. These are the Cybin volume levels down here. It's my mic level. So what if we wanted to do something more sophisticated, maybe based on time? Well, we could do something like this. Well, actually, we have a variable called Cybin.time. The reason we can get away with doing this, because this is actually doing I/O operations that are going to slow this down, but we have a ring buffer that Cybin fills. Cybin is not called in the actual Jack audio loop, so it's got like a latency built in. It's not technically doing things exactly in real time, but it's real time enough. You can't call Lua from an audio callback. It's not multi-threaded, so it gets a little bit hairy. But if we print this, you can see, okay, time is increasing. That's time in seconds. And we also have sample rate, which is 48 kilohertz. So if we wanted a sine wave that repeats 440 times in a second, we could say it's our standard Lua math library sinusoidal function. So we're saying, okay, 2 pi is 1 cycle. So if we multiplied it by time, oh, actually, we don't even need the sample rate here because we're not operating in samples. That would be really silly to do. So this would output 1 full sine wave every second, right? This is going to increase by 1 Cybin.time every second. We're going to move 2 pi every second. This would be too low frequency to hear. Multiply that by 60, we get like a bass tone. Oh, that was quite loud. If you multiply that by 440, we'll get a perfect A. So that's interesting. But that's not particularly useful on its own. Okay, so we can make a sine wave, nice. But we have everything in Lua at our disposal. So we can make our own sinusoidal oscillator. Let's do that. So what we're going to do is we're going to write a function that returns another function that returns a sine wave. The reason we're doing that is because we're going to use a language feature called a closure. So to understand closures, you have to understand globals. If we have a global x, right, equals 4, we can access it from anywhere. We can print it from here, but inside of this function, we could also print x, right? Great, cool. Why is that relevant? Well, if we instead had a variable local to this, a equals 4, right? We can define this. We don't have access to a, but anything in this function does have access to a. So if we wanted to keep track of state in our own function, we could say phase is 0. We could return a function, and the function we return will have access to phase or a, or whatever you want to call it, which means we can do this. So this or here means that if this isn't set, it'll be equal to nil, which is like null or some other, we don't have a value. Instead, it'll be equal to 440. So what we're doing here is we're setting phase to itself plus, if this was 1 instead of a frequency, this would, right, because we're dividing it by the sample rate, this means that phase would go up by 1 if it went in here was 1 every second. So 440 would be 440 times a second. We're going to use this here. We're going to divide that by 30 so we don't blow our ears off. So now we should be able to make a sinusoidal oscillator. So if we say S or OSC, let's not use crappy variable names, equals sin OSC, we should be able to return this. And now this is, remember we returned a function, but it has access to phase. And if we print phase, right, if we print phase out here, it's equal to nil. But if we instantiate this, yeah, there we go. And we can set the frequency, remember? Because it's going to default to 440, but the frequency is here. If we set this, it will override it. Nice. So that means we can do frequency modulation. Now, the problem with what we did here is we're dividing this by 30, which means that we don't have very good control over the amplitude. Well, not the kind of control that I'd like to have anyway. So we'll divide this by 30. Then we know we're modulating by 500 hertz. We can recreate these. Cool. Oh, that kind of hurts. Anyway, that's not super comfortable. So let's take this and try and make like a really bad growl bass. Okay, we've got bass. Let's have a bass frequency of freak. Can have the modulator run at a harmonic of freak. Just really modulate the crap out of it. Huge modulation amount. Helps if you set freak first. Awesome. And it might help if we distort it a bit. Atan gets, it's basically gonna make us look all logarithmic. You get above 1 and it starts tapering off really fast, so it emulates like soft clipping. So you can do... Yeah, listen to that. That's pretty cool. Let's mess with the frequency a bit. Cool, but what if we want to mess with the modulation amount? We can make another sinusoidal oscillator, right? Can we make it go wub wub? Alright, that's a serviceable growl bass. It's not that fancy. It'd sound better if we had some more subharmonics, layers, unison, filters, better distortion, reverb, other musical elements, sidechaining. But for a wobble bass from scratch, it's not bad. So yeah, that's a quick intro to Cybin, some basic synthesis from bass principles. I hope that's illuminating. I want to make some videos about installing Cybin, getting up and running, some more in-depth synthesis videos, maybe get some visual analysis tools so I can show a bit more rather than just telling. And I mean, listening to audio is great, but sometimes it's nice to have graphs. Yeah, nothing left to say. Hope you enjoyed this. Excited to make more videos like this. Hope that it recorded and came out alright. Guess we'll see. Peace out.